There's a guy, have you guys ever seen, I've mentioned this in a couple of times, I believe, I don't know if I mentioned it here, but 3 Blue, 1 Brown? I know I've mentioned it in 394, okay? 3 Blue, 1 Brown has a really good video on this explaining why the Gaussian distribution function and the natural exponential are related to one another and how it is sort of put together. But I'll draw this and we'll see something. So if I draw this sigmoid, right? And I draw this value along the edge here. If I mirror the sigmoid, what do I get? I get the normal distribution. The normal distribution is a volume by revolution of that natural exponential sigmoid, right? It is a decaying exponential from the mean out in each direction. So from the central value from mu of the distribution, or in this case we'd say, if this is x, we're going to say x bar, right? From this value, all of these are sort of names for this location, right? From this value we have a decaying exponential and a decaying exponential such that it is e to the negative lambda. You don't have to really understand all of the integral details of that mathematics in order to get what we're going to talk about here in just a minute. Okay, the more you understand this, the better we are though. So let's stick here for a minute and continue to think about this. If Fk is equal to the probability of a sample being within K, what does that mean? The probability of sample being within K is essentially its proximity to the expectation or the center value of the system. So it's more likely to be within a distribution the closer it is towards the mean of that distribution. You can understand this if we took it from this example, right, just real quick. If I have Kansas City, Missouri, right, at the center of it, and then I have population density, right, and it's gradually falling off toward the edges, indicated by increasing sort of topographic rings. If I place another city, Kansas City, Kansas, right, and I have the density of Kansas City, Kansas, I have the relationship between those city groups are two densities. This one's asymmetrical, this one's relatively symmetrical, right? If I place a value somewhere here in this region, I can associate whether I live in Kansas City, Missouri, or Kansas City, Kansas, based upon the density characteristics and the total prevalence characteristics of the sampling. So Kansas City, Kansas's population is lower than Kansas City, Missouri, but it's more dense, slightly more dense, okay? This kind of holds up, but not perfectly. We're just going to use this as an example. So I'm actually going to be characterizing these two systems based upon both the population and the relative density, right? So the density characteristic, the spread over which this occurs, is the function f, right? And the total value, that is all of the population within the Kansas City region, is your pi, right? That is the relative value for representation. So if I take those as a product, I now understand the change in value as it goes away from the mean of the distribution, as well as the total weight or the total amount of values that are described by that density function. The idea of using the prior as part of the product is actually a scaling factor. It's trying to treat all classes as relatively equally relevant with that respect. So if I take the product of prior times the density function, right, and I divide it by priors and density functions for all other classes. This is saying for all elements of K, 1 through K, I'm going to have pi 1, F1, pi 2, F2, pi 3, F3, pi K, Fk, right? So there's going to be, if this is a 4-class system, if pi 1, F1 or pi K, Fk up at the top, pi K, Fk is down here at the bottom as well, right? So this is total population, target over total population. But it isn't simply just the ratios of product, it's the ratios of likelihood relative to the prior estimation. So likelihood density relative to prior estimation. Now notice, am I utilizing any of the individual data points here? I mean individual data points. So my mechanisms of being able to assess error for this have changed, right? I can't really do what I was doing previously with regard to the error estimations. Right, so we're going to talk briefly about something and then we'll talk more about that error estimate. When I classify a new point relative to that density, I showed you some examples earlier on my other supplemental slides, but these are good enough for our purposes since you guys have already seen what I was talking about there. But I will have to pop back over to explain how LDA works in total by the time we're done. So, if I were to take pi, you see, notice pi's up there at the top on this left-hand side, pi's are identical. What does that mean?
We're taking the 50-50%.
They have an equal likelihood
Equal likelihood, why do they have equal likelihood?
because they're same density.
No, that's not density. This is just the prior. Just the prior. So what's that mean? There are the same number of samples in each of the classes, okay? This is a balanced data set, right? That's the key factor to keep in mind here. A balanced data set means that there are equal numbers in class 1 and class 2. So they're relative priors. Notice, if I take the area under the curve of each of these, the area under the curve is identical. Now, if I change the shape of that function, if I change the density, what happens? You have the same number of people over a wider area. What happens? The density drops. So I could have a curve that does this and a curve that does this, right? And they can have the same number of people. But people, persons, prior, per unit area, F, is a combination that describes the whole thing. How many individuals there are and how relatively closely packed they are to one another. Okay? We're going to make an assumption that they are symmetrical. We're going to make the assumption that they have that concentric ring pattern. They have that smooth distribution as part of a mechanism to be able to simplify our calculations here when we're working this by hand. What happens over on the right-hand side? Pi is 0.3, or pi 1.3, pi 2.7. What's going on there?
Number of data sample is 0.7 is higher.
What does this look close to? You guys remember the South Africa heart disease data? That's it. That's actually a very similar distribution to the South Africa heart disease data because if the red samples are the controls and the green samples are the case samples, the heart attack victims versus the general population, it's about that same distribution. It was a 70-30 split. It was 35, I think, but it was like 160 to 302 or something like that. But it's going to be relatively close to that. So what we see here is if we were to have this plot indicating the green for heart disease and the red for the standard population, we would be able to identify individuals that were at increased risk of the heart disease relative to whatever factor is being projected along the horizontal axis here as people moved away from this zero mean consideration, right, towards a negative value of some normalized factor, meaning that we rescaled it, right, to be able to fit in this system. We say as you get more and more negative, your chances of having heart disease in this populace would increase. So we see that at the value there, where the chances of having heart disease, right, versus the chances of not become equal to one another, we're going to set a line, we're going to set a boundary. We're going to call that our discriminant line, or a linear discriminant. So by applying first this operation to convert the data set into a density function, right? How do we do that? How do we convert the data set into a density function? Let's look here. I'm gonna pop forward and then we'll pop back and look at this again. This slide actually should be kind of maybe in a different place. I sometimes reorder these at the whim of what I'm talking about, so just bear with me. How do I get pi? All right, we already said I get pi by taking nk samples, that is the number of samples that are in k, relative to n. That's easy. All right? Notice, everybody's got hats on. It's a party. Party house. Okay? So once you stop doing the theoretical and start doing the practical, what do we have? Do we have the real pie? No. We have the best pie we can get. Okay? This is like, you know, the difference between like Perkins pie and one of those that comes in a little bag, right? The individual pies. Okay. So this is the best pie we can come up with based upon what we've got available. It's a simulation. It's a good enough copy, but it's only slightly representative of the true underlying real population density. What's going to happen is as the values of n increase, our estimate of pi is going to get better and better. So the more samples you have, the better your understanding of the actual fraction of population that prior represents. However, what's going to end up happening with that as well? As n increases, we have linear output, please. Back row. As we have a linear operation of increase in ratios, what happens there with regard to our calculations here? These all linearly increase in their op time, okay? So more and more samples, all of these things are going to take longer and longer to accomplish. I know it doesn't seem like much, but when you're adding together 1,000 samples, it seems fine. When you're adding together 1,000,000 samples, it starts to add up, okay? So calculating the mean densities for something like this, right? So we're calculating mu of k. This is the x bar or k bar, right? We could actually say k bar, the mean of that particular class. We say that it is the summation of all values of x over nk. All we've done is replace nk, or we've replaced the sample density characteristic, right? We said here now we're going to do the relative characteristics for the mean, or the arithmetic mean. So this is the arithmetic mean of just k. Just k. However, the next line is going to take a slightly different approach. This is x and mu of k, right? But it is x equaling k. So it is x of k for y of all k. So we start off here. When you see 2 sigmas, right, it often like oh, I don't like two sigmas. It's a nested for loop. It's a nested iterator. Okay? So go to the first sigma. So you arrive at the first sigma. It's going to pick one, pass it, and then operate on the next integrator. All right? And then it's going to iterate to the next item, pass it, integrate. So if I was to think about this, it's this for loop that says for all k, for k equal 1, right? Do add together all elements x minus mu sub k, or minus the mean of x, for that particular class. What is it going to do at the end? It's going to end up dividing them by all classes minus the value of the number of k cases. So it's going to take into consideration a norm relative to the value of standard deviation, right? So sigma is standard deviation. What do we do when we take sigma squared? We call this variance. So this is an estimate of variance. What does an estimate of variance allow us to do? Well, we're going to look at it in a minute and see how it plays in. But it can also be reworded in this way or reframed in this way by swapping out the estimate for sigma squared, or the variance of the system, relative to the summation of the difference between the sample n of k versus nk, which is actually pi up above, right? So pi and sigma squared have a relationship with one another that I think was one of those things that I can't really like show you a direct version of it or teach you a direct version of it. It's one of those things that you do, the more you do, you'll get kind of an intuitive feel for this relationship, because it's not one that, it's one that you can mathematically show, but it's one that's relatively interesting because prior applies to all potential samples, right? Prior is going to take the relative likelihood of a singular sample with respect to all other samples, or all other classes, right? So one class group relative to everybody within the space. And the sigma squared, the variance, is going to take into consideration the relative area over which those samples occur, right? So this is an entire density sample estimate. We're actually going to have the sigma square for this system, right, sigma square k, that can be rewritten as the summation for mu of k squared. Just calculate this system, right, and then say over, essentially over the inverse ratio of pi. What that means is, it's this number of individuals spread over this space relative to this other number of individuals spread over this same space. So if I spread them towards each other, their relative density ratios are a product of each of their representative likelihoods. It's a lot of crazy math to look at to explain, essentially 2 or 3 topics, yes.
So what's the capital K and the K is different? The small-
Correct. So this, keep in mind, anytime you see a capital, this is the vector version of it. Okay? When you see a lowercase, that is simply an iterator through the vector. So x is the random variable or the vectorized consideration, and some small x, big X vector, small x is a specific sample that is a member of x. Right? Big X is a vector which contains individual x's, right? And some x is a member of the larger set x, right? So when I say an individual x that is member x, that's what I'm referring to. I wrote on that piece of paper that I put over there. All right, we good now?
Yes.
The same follows for k, right? So we have k classes. If we have 5 classes, right, and I'm iterating through k, I'm going to be iterating through big K, right, not through small k. Small k is the specific member of big K that I'm on through the iteration. So I start on x1, x2, x3, so on.
So we are summing the big. So I have a question.
Yeah.
We are summing the big K.
We're actually summing small k,
Okay.
right? You see what I'm passing here?
Yeah.
This says k equal 1. What is this? What's the bottom of the sigma?
Starting.
Starting condition,
Yeah.
okay? What's on top of sigma? End case condition, all right? So big K, what is big K? When I talk about a set, what features does a set have if I'm entering it into a system? Cardinality, okay? Let's say set instead of, if I said array. So to borrow for the computer, for the computer science core, right? Array has size,
Yeah.
okay? So this is going to iterate, it's going to start at 1 and iterate through size of array K.
Array K. Okay.
Sort of on that point, this is sort of when you use the word vector, does that have the same utility and function and all that as a vector in other math, or are we simply talking about a list of?
Those are the same thing, but
Well.
they're the same thing.
Yeah.
When I say vector, I'm actually talking about either a column vector or a row vector. All right. So what is a vector in definition? It is a sequence of numericals with definite or indefinite length. If you're talking about a vector with regard to a angular calculation, you're talking about something that has magnitude and direction, right? That's just a specific type of vector. It's a tuple. All right. So the vector within like tensor vectors is a tuple. It's magnitude and direction. So it would be represented as 2 values inside the array. We're going to talk about an array of length n, right? That's just a longer array. So the first one is a 2D array, and then you could have a 3D. You could have a 3-dimensional vector, right? That has angle in 2 different spaces and the cross product of the vector of 2 previous 2-dimensional vectors, right? What is that? That's a tuple that contains 3 elements, right? It contains magnitude, direction x2. Keep going in a hyperdimensional vector. What do you end up with? 4, 5, 6. You end up with an array system that sequences off magnitude times angle in this dimension, angle in this dimension, angle in this dimension, angle in this dimension. Okay, so when I say they're the same, they are in fact the same because I'm describing this as a likelihood relative to the spatial characteristics. I could actually redraw a density function as a vector characteristic. because a vector is a function of motion or direction, or displacement, I guess you'd say. But it would be a function of displacement. That'd be a better way to say it. Does that clarify for you?
Yeah.
I'm just really dealing with, when I say vector, within regard to computer science notation, that's just a row of values that are all independent measurements or independent categories. In this particular case, the measurement that's being provided is that categorical variable, the label that's been placed upon the object. So if you think about it in that way, my data set is going to consist of a series of values that have been collected, and at the bottom of that system is going to be a label that's been put on it. If I think about the row across that system, that is going to be the summation of all possible assignments for the classes that can be assigned to it, right? Let's go to our apples, bananas, kiwi fruit, oranges, whatever. That's our fruit classifier, right? And so we're going to have a certain number of samples of each of those fruits. And then let's say we took pictures of them and we created some measurements of those. What color they are, how big they are, what degree of circularity they have. And then we fed them into the classifier. They would create a series of density functions relative to the overlaps between those elements, right? They would overlap in some dimensions and not overlap in other dimensions. And the degree to which they overlap versus didn't overlap would allow us to be able to determine the degree of kiwiness versus orangeness versus appleness of a roundish fruit, right? And then we have this other little group over here with bananas. They're yellow and don't have a lot of circularity, okay? So they're relatively separable. That would be a nice, tighter, separable group. But then we have a lot of things that are relatively similar to one another in terms of certain features, but separable with regard to others. So we get up in the higher dimensionality spaces, that's where it gets more complex. But I hope I'm elucidating with you how the math is working here, okay? We're just iterating through an array. That's all really each of these vectors are. If I say vector, substitute it with array in your head, and usually that's a pretty safe assumption. That good?
Yes.
Okay, cool. All right. Okay. All right, let's say why discriminant? We said that well-separated class parameters for the logistic regression model are unstable. What does that mean? Why would we consider them unstable? Well, there's an interesting aspect to the logistic regression that if I have a series of x's here, and I have a series of o's here, and I notice they're nice and easily separable, when I put my logistic in between them, right, notice, that's a good separability. What about this one? What about this one? What about this one? All of them work approximately equivalently well with regard to the threshold consideration of the 0.5. I can literally push the bar of the logistic function all the way over up against samples in one class group, and that function will return the same relative performance. So the instability of easily separable class groups is actually due to the indeterminacy of an optimal placement based upon characteristics of the sample groups they're dealing with. The placement of the logistic function, right, its center, its crossover point, is only relevant based upon its ability to separate this group from this group. It doesn't take into consideration the prior or the density characteristics of these distributions, merely handles the value of placing the discriminant somewhere that works with respect to the placement of these systems. So since I can technically have an infinite number of possible equally good assignments for the logistic regression in well-separated classes, it becomes unstable, meaning that you can actually get different answers depending on how you calculate it, right? Depending on whether you start from O's and go to X's or go from X's to O's, we'll actually end up with different discriminants. That level of uncertainty makes it relatively poor whenever you have multiple open spaces within your class groupings. However, if I start placing O's here, well, that's a small one. If I start placing O's here, X's here, right, and I start placing some X's over here, some O's over here, it gets a lot easier for us to go, okay, where does the density transition, right? I can say that it's going to be increasing likelihood of X, right? Or increasing of likelihood of O, decreasing likelihood of X. I can say, yeah, that would make sense, because there's only one that will satisfy an understanding of the equal likelihood based upon the numbers that are provided. When they're well separated, it doesn't work great. When they're overlapping, it's actually pretty daggone solid, all right? Sometimes maybe even better than linear discriminant analysis. Linear discriminant doesn't tend to suffer from that problem except for higher dimensions, where it becomes a little bit ill-posed as to where we're going to place the discriminants, but it doesn't have the problem of taking into account the density, because it's using that Bayesian inference. It's using the understanding of prior and density estimates to make its understanding of the system. When small n is occurring, right, that means whenever few samples are present, and p, predictors x, have approximately normalized, right, have approximately normalized distributions in each relevant class. Linear discriminant model is, again, more stable than the regression model. So why would small n normal distribution have problems with respect to the logistic discriminant? Well, small n is difficult to be able to generate density estimates, or density normals for when you have no understanding of distribution prior. The logistic discriminant does not take into consideration distribution prior. It doesn't actually know what the prevalence of that class is. So it's going to essentially try to place them based upon the symmetry of a very few samples. So if I can't estimate the density or joint likelihood for some specific interval space by having enough samples in some region in order to be able to calculate that likelihood for each class space, right? The transition space here, the slope of the system, takes into consideration sort of a window and tries to understand the necessary slope through that window. With the LDA, it takes into consideration the entirety of the population relative to the entirety of the alternative population in order to build the density functions, right? The density functions get built separately outside the system. Logistic utilizes the specific samples themselves. So because it utilizes the samples themselves, means it's susceptible to failure or poor performance whenever there aren't enough samples to adequately define the space itself. I had somebody that asked yesterday about this idea of what is too small of an n, and the answer is usually something that's in the tens or hundreds, but there's a lot of other factors there at play, because it is samples per unit density. So if the range over which a specific class occurs is pretty wide, if it has a high entropy, and there are few samples, it's related to something that my guys in the front here will know. It's related to Nyquist's rate, right? It's related to the sampling rate characteristics of a frequency aspect. So if you have a periodic signal, right, and you're thinking about the full sequence of that periodic signal, you have to make sure that you're able to sample at least twice, right? So we have a frequency target of greater than two times the frequency of the underlying system. So if this is the frequency characteristic, if this is the density characteristic, frequency and density are two sides of the same coin, right? Frequency is how often this thing changes. This is how much it changes per relative unit period, right? This is the spatial version. This is the time domain version. So frequency estimates for Nyquist sampling rate tell us how many samples we must have at a minimum to understand the underlying fundamental distribution of changes within the system. There's actually a relationship between probability functions and Nyquist rate. Like it was derived via the use of different frequency rates based upon frequency density. So that, I know some of the CS guys, you're probably not gonna, you're like, what's Nyquist rate? I don't know. But for, the rest of you might understand how that ties together. But if I have enough samples per unit area to be able to adequately describe the underlying mechanics of how the system is changing, then I can utilize the logistic regression. Otherwise, I'm going to have to come up with a continuous function that describes the space based upon that small number of samples, right? I can assume a normal distribution with only I had to grab the one marker that doesn't work. I could have only a few samples, right? Only need a few samples in order to make an assumption of normal density, right? But with too few samples, it becomes very hard to determine, right, where the samples occur in each of these spaces. The logistic will have a harder time finding the center of these spaces than the linear discriminant will. It becomes more indeterminate, unstable again. Everybody clear with what I'm talking about there? Okay. The linear discriminant analysis also is more popular when we have more than two responses. Now let me say this. It's not impossible to do a multi-logistic regression. We showed actually with the multinomial, that's what is called a multi-logistic regression. So the multinomial regressions are actually a thing, right? They're done in certain spaces. Usually they're done whenever there's a lot of overlap, okay? Lots and lots of overlap and few classes, usually less than 4, they're okay. Matter of fact, they can theoretically outperform LDA. Theoretically. If all the planets align properly, you can sometimes have a multi-logistic that will outperform an LDA. I've only ever seen it a couple times, but it does happen, it's possible. So when we say LDA is better for more than 2 classes, this means that I can actually project more than 2 classes on a space and maintain an understanding. So we said previously, if this is our sample space and I have a logistic regression, I can't cut the space off and create multiple bins, right? That doesn't work. But if I reproject the space as a density function, and then I take density characteristics and I apply the mechanism we're going to discuss in a minute, I can actually place multiple classes on the same space. Class 1, class 2, class 3. And now they become separable based upon their likelihoods as you travel across the distribution space. So this mechanism allows us to be able to solve problems in a slightly different way, all right? This is Gauss's law, all right? Actually, Gauss didn't really come up with this, but there were a couple mathematicians afterwards that took some stuff that he did, and then because they really loved him, they said, here, you can have this. So it was a posthumous, essentially, award for his work in the understanding of distributions and mechanics. But the density function estimate as provided here says that a natural exponential representation relative to the square root of 2 times pi, what happens there? That's the revolution. That's the surface of revolution. So I'm describing the density function as a surface of revolution of a decaying natural exponential. That's all that's happening, yes?
Is rho part of the 2 pi under the square root
Sigma?
there? Or sigma, sorry.
Sigma? Yeah, what?
Is it under the square root?
Yes,
It
yes.
is? Okay.
Yes.
I want to make sure that I get
Yeah.
that under there.
Yeah, the bar doesn't travel over, but you know what? I'm not really even sure it matters. I don't think it matters.
You're not gonna make
square
this
root
calculate just
square root
by
2
hand?
pi times sigma versus 2 pi sigma square root. No, I don't think it makes a difference. I'll look and check and see if it makes a difference, but I don't think it does. But I assume that they're all underneath the bar because that's one product that's a square root product.
So do we need to calculate by hand using
No.
the Youngster?
No, matter of fact, this is all the further we're going to look at. Notice, I can substitute F, right? I can substitute F with an assumption of Gaussian density. Now watch this. This is the cool part. Apply mathematical trickery, and you actually get this. okay? Expand it, cancel a bunch of stuff, so blow it up, cancel a bunch of things, and awesome, okay? We get a impulse function, this little delta here. It says delta 4K. This is discriminant score. I'm going to talk about something real quick. I'm going to go over to my other slides here. Come on. We only have like 2 minutes worth, but I want to describe something for you. Okay, previously we were talking about projections of the LDA. We've seen this slide, we talked about this slide. All right, so let's go forward a second. We talked about these 2 slides, right?
Yes.
How the reprojection works. Let's talk about what happens in the actual algorithm of the linear discriminant. We're double optimizing now, okay? This says sigma relative to an axis of orientation. Let's talk about some shadow puppetry for a moment. Different angles or different axes of vision change things, okay? Are my fingers separated? Yes. Right? You don't know to begin with. You can't see it. This is the essence of stage magic, right? You can't see it because it's planar, and then I turn it and it becomes 3D, okay? The separability, what happens to the separability? Let's say that this is a 5-class system. What happens to the separability as I rotate this space? Right? It changes, right? Notice the projections of each of my fingers maximizes when I'm normal to the surface and minimizes and overlaps maximally, okay? Did you just have that moment you go, oh man, this is obvious, kind of?
No, I just had that flashback to ME 130 graphic design because we're doing normal faces and orthogonal views and stuff.
Not quite that bad. We have the spread in one class, right? This is how far apart. We can think about it as the distance from distance from here to here, the spread across the class, right? The spread across the class changes as I rotate. So I have class 1 and I have class 2. Those are the sigma. Those are the deviations, or this relative spread of each class. Maximization function over there. What's happening? Let's look at 2 things. First, we have the mean of the class 1. We have mean of class 2. The difference between these is the magnitude of separation between each of the classes. I place their means as far apart from one another as I can. I then take the square of that, right? What's that turn it into? Absolute magnitude. Then I divide it by what? Each of the relevant sigmas of the classes of interest. If I maximize that function, I've satisfied 2 constraints simultaneously. I've maximized the between class spread delta mu, and I've minimized the within class spread sigma, right? I want to get each of the classes as tight to one another as they can be, and I want their centers to be as far apart from one another as possible. I'm going to start and I'm going to rotate a surface, or I'm going to flashlight and a surface, and I'm going to rotate them around the space such that I come up with a surface that maximizes for that double optimization. I only actually have to maximize this one ratio in order to maximize that double optimization. That is how the linear discriminant analysis works, and it is called an informed feature extraction methodology. By rotating the array of the data, I have changed nothing. The relationships stay the same, and the internal representations stay the same. However, I can have a singular dimension, one dimension, that can be represented or can be pared down from a previous 2-dimensional system, such that I have a new axis that optimally separates the 2 classes from one another. Okay? Thank you for the extra couple minutes. Have a great weekend. We'll continue talking about this, and then we'll enter off into metrics by which we calculate. We'll look at the what's called a confusion matrix. All right, I love this. It's a great name because that's what it induces. It induces confusion. Okay, so we'll talk about the confusion matrix, and this is the mechanism by which we assess the quality of classification algorithms. Because as I said previously, classification algorithms, simple accuracy is not sufficient. There's actually 4 types of accuracy that each classifier can have, and they change relative to the way in which the system operates. So, have a great weekend.
Thank you. You too. Do you want me to send you an email for changing the due date on that lab?
It doesn't matter exactly, so it doesn't matter.
Okay.
They stay open.
Oh, they do?
I don't close them. I actually never intended to close the first one, it just happened.
Oh, okay.
So I usually leave them open. So, and if it doesn't, I consider it Monday. I'll do it so everybody else can relax.
Okay.
Thank you.